Good morning, students. Today we'll continue Fredholm first theorem. Yesterday we had derived the Fredholm first series, which gives the value of d lambda in the form of a power series. Now we are ready to solve the Fredholm integral equation gs is equal to fs plus lambda integral a to b kst gt dt, and we will express the solution of this equation in the form gs is equal to fs plus lambda integral gamma st lambda ft dt. Here gamma st lambda, that is the resolvent kernel, which is given by the ratio of two entire functions dst lambda and d lambda. Now we will use the property of the resolvent kernel, which is given by gamma st lambda is equal to kst plus lambda integral ksx gamma xt lambda dx. By using this property and substituting the value of the resolvent kernel gamma in the form of the ratio of two entire functions dst lambda and d lambda, so the equation which we get, that is given by dst lambda is equal to kst into d lambda plus lambda integral ksx dxt lambda dx. Now as we can see that the series Fredholm first series, which is for d lambda, that is a form of power series, so we will have to find the solution of this equation also in the form of a power series. So let us consider the power series for dst lambda in the form c naught st plus summation p varies from 1 to infinity minus lambda raised to the power p divided by p factorial into cp and also we can write the Fredholm first series which we have obtained already for d lambda in the form of the series d lambda is equal to c naught st plus p varies from 1 to infinity minus lambda raised to the power p divided by p factorial into cp. As we can see from the Fredholm first series, the value of this c naught, that is 1, and the value cp from there, that is the integral p times of the function k, which is s1 s2 s3 sp in the first row, and in the second row also we have s1 s2 s3 sp. This notation we have discussed already. This integral is with respect to s1 s2 s3 and so on with respect to sp. They are p times integration. Now substituting the values of d lambda and dst lambda from these two equations in the equation e, substituting the values there, we get the expression of this form, and now this equation can further be written in another form, which is given by c naught st plus summation p varies from 1 to infinity minus lambda raised to the power p divided by p factorial into cpst is equal to kst into 1 plus summation p varies from 1 to infinity minus lambda raised to the power p divided by p factorial into cp plus lambda integral a to b ksx into minus summation p varies from 1 to infinity minus lambda raised to the power p divided by p factorial into p into cp minus 1 xt dx. Now comparing the coefficients of like powers of lambda on both sides, if we compare the constant terms, we can see on the left hand side the constant term is c naught st and on the right hand side this term is kst. Now for minus lambda raised to the power p divided by p factorial, on the left hand side its coefficient is cpst and on the right hand side the term with minus lambda raised to the power p by p factorial is kst into cp minus integral a to b p ksx cp minus 1 xt dx. Now we put p is equal to 1 here in this equation, the left hand side becomes c1 st, on the right side we get kst into c1 minus integral a to b ksx into c naught xt dx. Now using the notations, what is c naught xt? C naught xt is the kernel kxt. So substituting the value, also substituting the value small c1 by using the definition of small cp, which we have already used. So c1 is integral kxx dx. Substituting the value small c1 here, we get the value of capital C1, which is given in this form. We can combine these two terms under the one integral sign. So we get the value of capital C1, which is given by integral a to b kst into kxx minus ksx into kxt dx. Now, this can further be written in the form of a determinant. This expression, if we write this expression in the form of determinant and using the notations which we already defined, so using the notations, this determinant can be written in the form k sx dx. Now, substituting this value in the equation j, we get the value of capital C1, which is given by integral a to b of the function k, which is the function of the variables sx in the first row and tx in the second row. Using the same, we can find the values of c2, c3 and so on, capital Cp. c2 is given by the double integral of this function, and in general Cp is given by the p times integration of this function k. In the first row we have the variables as x1, x2, x3 and up to xp, and in the second row we have the variables t, x1, x2, x3 and so on up to xp. Now substituting the value of capital Cp in the equation f, we get dst lambda is equal to kst plus, here we have substituted the value of capital Cp. Now till yet we have obtained the value of the function dst lambda in the form of this series. Now it remains to prove the uniqueness of the solution. So let us take GS with the solution of the given Fredholm integral equation of second kind. Now replacing s by x, the Fredholm integral equation can be written as gx is equal to fx plus lambda integral a to b kxt gt dt. Now multiplying this equation throughout by gamma sx lambda and integrating between the limits a to b with respect to x. So left hand side becomes integral a to b gamma sx lambda into gx dx. On the right hand side, the first term becomes integral a to b gamma sx lambda into fx dx, and the second term after doing the integration, that will take this form. Now we again use the property of resolvent kernel. Resolvent kernel satisfies the equation gamma st lambda is equal to kst plus lambda integral a to b ksx gamma xt lambda dx. So let us substitute this value in the above equation in the left hand side. So if we substitute the value here for this gamma, we get the equation in which these two terms are cancelled out, and we get integral a to b kst gt dt is equal to integral a to b gamma sx lambda fx dx. Now we can substitute the value of this expression in the given Fredholm integral equation of second kind. After substituting the value there, we get gs is equal to fs plus lambda integral a to b gamma sx lambda fx dx. Now we can write this equation, we can write the solution in the form by replacing the variable x by t. So if we replace x by t, the solution takes the form gs is equal to fs plus lambda integral a to b gamma st lambda ft dt. And this solution, which we have already proved that this kind of form is always unique form. So this proves the uniqueness of the solution for the given Fredholm integral equation. So this completes Fredholm first theorem, in which we have obtained the solution of given Fredholm integral equation. In that case, where the kernel and the function f, they are any integrable functions.